Today I'm going to talk about the next part of this unit, that is root locus technique. Well, root locus technique is useful to aid control design and analysis. This in fact is a graphical technique that gives a qualitative description of the performance of a control system. So it graphically provides a range of stability, range of instability, transient performance of the system based on location of closed loop roots. In root locus technique, a design parameter k is introduced into the system. This parameter is varied from 0 to infinity, and the locus of the roots of the characteristic equation are drawn. And thus root locus is a graph showing locus of closed loop roots in the S-plane by varying a system parameter loop gain k. And this again is usually incorporated in forward path. And the reason that we employ this method is that the closed loop control system are difficult to comprehend from qualitative point of view, and hence they rely heavily on mathematics. And by transient performance, we mean the oscillations, peak time, overshoot, settling time of the system, etc. So shown here is the S-plane portraying different values of natural frequency of oscillation omega n, and for different zetas, so for different values of omega n, you have different circle of different radius, and for different zetas, you have line going growing out from the origin radially. For example, shown here are lines corresponding to zeta equal to 0.2, zeta equal to 0.5, 0.8, and 1. So with this basic idea, we can choose a point where the system, we think that the system roots should lie. For example, if you want to choose system to have zeta equal to 0.5 and omega equal to, let's say, omega n3, then this is the point where the roots should be lying. We also saw that for different values of zeta, the waveform of the system, the output waveform of the system varies accordingly. So it's shown here. So let me make this more clear by giving you an example. Suppose that you're working in a car manufacturing company and your boss says you to design a car that does not give any jerks at all while going over the speed breaker. You know that in order to manufacture such type of car, you need to have suspension system, that is shock absorbers or shockers, that are capable of absorbing the shocks completely without giving any oscillations. That is, you would like to keep zeta close to 1 but greater than 1. But to design a suspension system that does not that does not give any oscillations at all, you have to fit a damper that drains all the jerks. You also knew that in such a case where zeta is greater than 1, that is, damper drains all the jerks, the damper will soon lose its capabilities. So you are able to convince your boss that the dampers in the suspension system of such vehicle cannot survive long in the condition of the roads that we are having, and sooner they will require a change. Thus you explain that in order to avoid such problems, you have to do a sort of trade-off between oscillations and damper life. And your boss says, okay, I can tolerate only 15% of overshoots. So from this basic idea, 15% of overshoot, now you evaluated the value of zeta corresponding to 15% overshoot and say you get zeta equal to 0.85. Thus we try to model the suspension system of the vehicle, so which comprises of a mass, a spring and damper, a dashboard. So we come with an equation which is given as follows. Since going over a speed breaker is a sort of impulse response where you provide input for a very short duration of time, and hence the mathematical relation for the same can be written as ms square plus bs plus k equal to 0. And from this we can obtain the expression corresponding to s equal to minus b plus minus under root b square minus 4 mk divided by 2m. And I will try to plot this the locus of the s for varying b. You drew the root locus of the roots on S-plane by varying b from 0 to infinity, and what you got was something, a graph shown over here. So when you varied b from 0 to infinity, this is how the behavior of the plot was obtained. Now, since you assume that the mass that will be put on the suspension system is known, the spring constant is known and fixed, the only thing that you can change is the value of B. Thus, by varying this value of B, you observe that the roots move in this fashion. So in this particular system, we consider B as a design parameter which is allowed to be varied or changed in order to attain the desired response of the system. Thus, we say that the root locus is the locus of the roots when a design parameter of the system is varied. Now, when we look into the lines corresponding to zeta equal to 0.85 on the root locus, we observe that the lines corresponding the lines for zeta equal to 0.85 are something shown over here, and thus the points that we want our system to have so will be somewhere here where the lines crosses the root locus. So these are the points which we want our system to be taking the values of zeta as well as omega n. So if you draw the circle corresponding that passes through, if you draw a circle that passes through these 2 points, then that will give you the value of omega n as well. So knowing the value of omega n and zeta, you can easily conclude the value of the dashpot B. With this basic concept in mind, let us now try to draw the root locus with the basic steps by hand. We drew root locus on the software like MATLAB, but sometimes it is required to understand root locus to know how to draw them by hand. So that is why we are going to discuss the steps that are involved. So as I told you that whenever you are required to find the root locus of any system, what you do is you introduce a design parameter k into the system. So if g and h was the part of the original system, and you'll have to introduce the design parameter k, and you will have to vary this parameter from 0 to infinity in order to obtain the locus of the roots of the system or the characteristic equations. So the step number 1 says that you'll have to obtain the characteristic equation 1 plus k g s h s of the system in the form 1 plus k q s by ps. So for example, if suppose that you're given gs by this transfer function and hs by this function, then 1 plus k g s h s can be written as 1 plus k g into h will give you this function. So this comes in the form of 1 plus k q by p. So this is what is required in the first step. Now the second step says that you'll have to locate the poles and zeros of gs hs on s-plane. So the poles and zeros of GSHS. So if you see that this function G is GSHS, s plus 2 upon s plus 3 into s plus 5 into s plus 1. So from this we get 1 0 s equal to minus 2, which is located here. And then we have 3 poles s equal to minus 1, minus 3 and minus 5. So they are located at their respective positions. So we have 3 poles and 1 0. So the poles are given in green and 0 is shown in red. So this is the step 2. Now step 3 says that the number of branches that the root locus will have will be equal to the number of closed loop poles or zeros, whichever is greater. So in any system, if you're going to have the number of poles or zeros whichever is greater, that will give you the number of branches that root locus will exhibit. For example, in this particular case, if we see we have 3 poles and 1 0. So the root locus, the final root locus that will come for this particular system will be having 3 branches because the number of poles are 3, which is greater than the number of zeros. Had the system have number of zeros greater than the number of poles, in that case, the number of branches will be equal to number of zeros. Rule number 4 says that starting from far right, the part of real axis lying to the left of odd number of poles, odd number of roots, which may be poles or zeros, up to the even root or infinity if none found will be the part of root locus. So this rule says that if you're going to start from the far right, and you will have to identify the odd number of roots. For example, in this particular case, you have this as the first root, which is nothing, which is a pole, and this as the third root. Then the zero is this zero occurs at second position. This pole occurs at fourth position. So you'll have to identify the odd number of roots in the on the S-plane which lie on real axis. And this rule says that to the left part of the real axis, the part of the real axis lying at the left side of the odd number of root will be the part of root locus. So this part of the real axis will be the part of the root locus. So this is what rule number 4 means. Now rule number 5 is breakaway point or break-in point. So on the root locus between two open loop poles, if the root locus exists between them, as the gain factor is increased, the roots move towards each other till they are coincident for a particular value of k. On further increasing, the value of k breaks the root locus in two parts at 90 degrees. So the breakaway point can be determined by rewriting the characteristic equation in terms of k and solving it for the values of s for the condition d by ds of k equal to 0. And breakaway points are called when we talk about poles, and the term break-in point are said when we are concerned with zeros. Now note that the poles leave the real line in search of an open loop zero, and if there are not enough zeros to make a pair, then the extra lines or the branches go to infinity. For extra zeros, the lines or the branches come from infinity. So breakaway point, as we saw in the example of the suspension system of the car we were trying to design. So we saw that the roots of the system started from the imaginary axis, moved towards the real axis, and there was a point where they clashed. So that particular point is called as breakaway point, and from that point the two roots or the poles moved in the opposite direction. Well, had these been zero, then they would have been arriving from infinity, crashing at the same point and coming to the imaginary axis. So breakaway point are the terms used for poles, while break-in point will be used for the zeros of the system. Now the rule number 6 talks about the angle of asymptotes. So what are asymptotes? Asymptotes are drawn for curve, and asymptote of a curve is nothing but a line such that the distance between the curve and line approaches zero when they go towards infinity. So asymptotes come into picture when there are extra poles or zeros which are unpaired. Since the root locus for unpaired roots will go to infinity, thus to know that at what angle they go to infinity, asymptotes are drawn. And they are given by this expression. Phi is 2k plus 1 into 180 divided by np minus nz, where k is 0, 1 up till np minus nz minus 1. So if you look at this particular figure, which is nothing but the same root locus that we took from our previous example, so we saw that the poles which were initially on the imaginary axis, they moved towards each other. On real axis they met. So this particular point is termed as breakaway point, and after meeting at this point, one of the pole went towards left side, the other towards right side. So one root moved towards left to infinity, and since this example didn't have any zero, so both the poles were unpaired, and that is why the poles went on either side, on the opposite side. One of them went to infinity, the other is going to origin. Also, the number of asymptotes will be equal to the number of unmatched pole zero pair And now we talk about the rule number 7 says the rule number 7 pertains to the intersection of asymptotes on real axis. The asymptote subtends certain angle from the real axis at a point given by x, which is equal to summation poles minus summation zeros divided by np minus nz. So we'll try to implement this rule when we solve an example in the upcoming slides. Rule number 8 says the intersection of curves with the imaginary axis. So rule number 7 is in continuation to rule number 6, where we talked about the angle of asymptotes. Since in rule 6 we find the angle at which the asymptotes will be drawn, but at what point on the real axis they should be started or they should be drawn from comes from rule number 7. So the intersection of asymptotes is given by rule 7, and rule 8 talks about the intersection of curve or the root locus with imaginary axis. So if you look at this particular figure, we have three poles, and when we vary k from 0 to infinity, so at k equal to 0, these poles are shown in red. So the location of the three poles in red are corresponding to the values of k equal to 0. When k is increased, so as you start increasing k from 0 to infinity, so these two poles will one of them will these two poles will move towards each other. They will clash at a point, or this point is called as breakaway point, and will move in the direction shown by the branches towards infinity, while the third pole will move towards the left side of the real axis to infinity. So while they move towards infinity, these two poles, they will cross the imaginary axis of the s-plane, and these two points, this point and this point, will be termed as the intersection of curve with imaginary axis. So these points are found by uh, obtaining the value of k, and the point at which the root locus branch crosses the imaginary axis is determined by applying Routh-Hurwitz criteria to the characteristic equation, from where we obtain the auxiliary equation. So once you obtain the Routh table in terms of, you'll be obtaining some expressions in the first column of the Routh table in terms of k, and those expressions will be, since we learned that if any value on in the first column of the Routh table is going to be 0, and there are no sign changes above that 0 and below it, then that case corresponds to the situation of critically damped system, and thus we'll try to evaluate a value comprising of k in the first column of the Routh array, and are going to equate that term with 0. From there we'll be obtaining the value of k and substituting that k in the auxiliary equation from the row taken previous to the 0 value. So this is something that has already been taught in Routh-Hurwitz criteria, and we'll simply be implementing when we do an example. So once the Routh table is obtained, the first term involving k in the first column is equated to 0, which gives the value of k corresponding to the intersection of root locus with imaginary axis. And feeding this value of k in the auxiliary equation will give the value of roots at the intersection. And then comes the rule 9. It talks about the angle of departure from complex poles. So whenever in any case you're going to have complex poles, for example, if you talk about this example, then you see that there are two poles lying on real axis. Well, there are two poles that exist in complex conjugate form. And as I told you that if there is going to exist any pole in complex form, it will always have its conjugate on the s-plane. So these are the two complex poles, and whenever we vary k from 0 to infinity, so like these poles, they move towards each other, meet at a point, breakaway point, and then go to infinity along this branch. Then likewise you'll be having these two poles, they will be moving in the direction shown by the branches. In fact, these two poles will be moving exactly as a mirror image about real axis when you vary k from 0 to infinity. So we'll try to find the angle of departure, or the angle at which they depart along the branch. So that particular angle is tangent to root locus. So phi d, the angle of departure, is given by the expression 180 minus phi p minus phi z, and this is phi p and phi z are computed by the poles that are remaining. For example, if we want to compute the angle of departure for this particular pole, then we'll be connecting this pole with all the remaining poles and zeros. And for phi p, we'll be computing this angle, and then we'll be computing this angle and this angle, which is nothing but 90 degree, and we'll be adding these three angles because these angles are subtended from the remaining poles, so they will contribute to phi p. Had this system have a zero, let's say we had a zero somewhere here, in that case we would have measured this angle and let's say theta or 30 degree. So this angle would have contributed phi z, and after substituting the value corresponding to phi p and phi z, we compute the angle of departure phi d. Once the angle phi d is computed, then it's time to draw it. So phi d is drawn with respect to the reference which is taken along the x-axis. So for example, if you want to draw the, phi d for this particular pole, then you'll be choosing a reference which is drawn parallel to x-axis, and from this reference, if suppose phi d came out positive using this equation or this expression, let's say phi d came out as plus 30 degrees, then phi d is measured positive anti-clockwise, and while it is measured negative clockwise, and thus if suppose that you came with the value of 30 degree, then the positive will be drawn, so you'll be drawing an angle 30 degree, sketching a line at 30 degree from the reference. This means that the pole will be moving, this pole will start to move along the this line. So in fact, if you talk about this example, so pole moves minus 90 degree from the reference. And let's talk about the example that is given here. So in this particular case, if we see that if we try to obtain the angle of departure, it must have come out equal to minus 90 degree, because the pole moves at an angle of minus 90 degree from the reference. So the pole should have started to move along this line, which is the angle of departure, and will go along the asymptote from the probably from rule number 6 and 7. So after obtaining the asymptotes and the angle of departure, we conclude that the complex poles starts to move along the angle of departure, and finally go along the asymptotes that we will be obtaining. Likewise, when we talk about the angle of arrival for complex zeros, so angle of departure will be for complex poles, while angle of arrival for complex zeros. And this is what we learned, that when we vary k from 0 to infinity, it is the pole that moves from its initial position to a final position. While when we vary k from 0 to infinity, zeros come from the final position, or from infinity, or from pole. So they will become the branches from the infinity, or the poles will be coming towards 0 at k equal to infinity. So the motion of the branch in case of poles and zeros are opposite. When you vary k from 0 to infinity, poles start to move from its initial position to infinity or a 0 at k equal to infinity. While if you talk about 0, when you vary k from 0 to infinity, then zeros will be coming from infinity, and will be reaching a position at k equal to infinity. So this will be clear when we do some examples based on both poles and zeros. So angle of arrival is given by the expression phi a equal to 180 degree minus phi z minus phi p. So very similar to the angle of the uh, the angle of departure, we will be computing phi a. For example, shown in this example, we have two complex zeros. So in order to compute the angle for this complex zero, we'll be doing the same process that we did for a pole. We'll be connecting all the roots with this particular zero for which the angle is to be computed, and we'll be calculating the angles corresponding or the angles between the zero and pole separately, and that of 0 and 0. So all the angles which are contributed by the zeros will give us phi z, while phi p will be contributed by the poles that are available in the S-plane, and thus by substituting the values we can obtain phi a and draw it as we did for the angle of departure. So now we summarize the rules that we learned. So the first rule in order to draw the root locus was to obtain in the form 1 plus k qs by ps. The second rule was to locate the poles and zeros of gs hs on S plane. The third was uh, to observe the number of branches that the root locus will have, and that will be equal to np or nz, whichever of them is greater. The fourth rule says that the part of real axis to the left of an odd number of roots will be the part of root locus. The fifth rule talked about the breakaway point or the break-in point, which was given by the differential of k with respect to s equated to 0, and thus from this we can obtain the values of s for which the locus would be, or the poles will be uh, clashing and moving in the opposite directions, or the zeros will be clashing. And rule 6 says the angle of asymptote is given by phi by this expression, and then the intersection or the point from where the asymptotes on real axis will be drawn is given by this expression x, which is summation poles minus summation zeros divided by np minus nz. Eighth rule talks about the intersection of curve with the imaginary axis. So whenever you draw root locus, the curve might be crossing, and most of the cases the curve may be crossing the imaginary axis, and for this we evaluate the values of s from the auxiliary equation obtained from the route table. The angle of departure from complex pole is given by phi d by this expression, and the angle of arrival at complex zeros is given by the expression phi a. So these are the rules that we'll be using in order to obtain the root locus for any problem in hand. And in the next lecture, we'll talk about, we will do some examples related to root locus, and we'll try to draw the root locus by hand, as well as we'll try to confirm that the plots are correct using MATLAB.